Hello everyone, I am MS Srinath, currently pursuing my BTech first year from Institute of Aeronautical Engineering. I hope you all are fine. Today I am present before you to share my tech talk topic, that is advances in polymer integrated optics. Let's start. The topics which we are going to discuss today are: what are optical fibers? What are polymers? What are optical polymers? What is integrated optics? What are the polymer integrated optics? Chronological order in the development of polymer integrated optics and advances in the polymer integrated optics. Let's start. Optical fiber. What is an optical fiber? An optical fiber is a fiber made from thin strands of either glass or plastic. It has little mechanical strength, so it must be enclosed in a protective jacket. These protective jackets provides it with mechanical support so that it doesn't break. Often, two or more fibers are enclosed in the same cable for increased bandwidth and redundancy in case one of the fiber breaks. It is also easier to build a full duplex system using two fibers, one for transmission in each direction. Given here is an example of structure of optical fiber. The center one is called core, which is surrounded by a layer called cladding, which is surrounded by jacket. This jacket provides rigidity to the core. Next five. Next system. The signal source is connected to optical transmitter with a copper cable. The optical transmitter is connected to optical receiver with a fiber optic cable. The optical receiver is connected to signal destination with copper cable. Types of fiber. Both types of fibers described earlier are known as step index fibers because the index of refraction changes radically between the core and cladding. Graded index fiber is a compromised multi-mode fiber, but the index of refraction gradually decreases away from the center of the core. Graded index fiber has less dispersion than multi-mode step index fiber. Fiber optic cables. There are two basic types of fiber optic cable. The difference is whether the fiber is free to move inside a tube with a diameter much larger than the fiber or is inside a relative tight fitting jacket. They are also referred as loose tube and tight buffer cables. Both methods of construction have advantages. Loose tube cables. All the stress of cable pulling is taken up by the cable strength members, and the fiber is free to expand and contract with temperature or whenever required. Tight buffer cables are cheaper and generally easier to use, but they cannot expand or contract like loose tube cables. Given here are structures of construction or structures of loose tube cable and tight buffer. In loose tube table, the core is at the center, which is surrounded by a layer called cladding, which is then surrounded by a layer called fiber buffer, and there is a huge gap between tube and fiber buffer, which is surrounded by air or gel. This air or gel provides it with support whenever the fiber needs to expand or contract. And at tight buffer construction, the core is surrounded by cladding, which is surrounded by fiber buffer, which is surrounded by plastic buffer, which is surrounded by Kelvar strength member and is wrapped by plastic jacket. As we can see, there is no air or gel in tight buffer. It cannot easily it it cannot expand or contract with temperature or whenever required. Hence, it is much cheaper. Polymers. A polymer is any of a class of natural or synthetic substances composed of a very large number of molecules called macromolecules. These macromolecules make molecules. Macromolecules are multiples of much simpler chemical units called monomers. Polymers make up many of the material in living organisms and are the basis of many minerals and man-made materials. Here are examples of some structure of polymers. Optical polymer. What is an optical polymer? Chronology of polymers and plastic optical fibers, or POF, or polymer optical fiber, is an optical fiber that is made out of polymer. Similar to glass optical fiber, POF, or polymer optical fiber, transmits light for illumination or data through the core of the fiber. Integrated optics. What is integrated optics? Integrated optics is a technology which aims at constructing so-called integrated optical devices or photonic integrated circuits or planar light wave circuits containing several or many optical components which are combined to fulfill some more or less complex functions. Polymer integrated optics. Why was there a need to combine polymers with optics? The demand in the demand in optical networking for photonic components that meet performance criteria as well as economic requirements has opened the door for novel technologies capable of high yield, low cost manufacturing while delivering high performance and enabling unique functions. This is done by integrating the polymers with optics. The most promising new technologies are based on integrated optics. Integration permits the parallel production of complex multifunctions, photonic circuits on a planar substrate. Polymeric materials are particularly attractive in integrated optics because of their ability to be processed rapidly, cost effective, and with high yields, because they enable power efficient dynamic complementary through thermo-optic and electro-optic acquisition, and because they allow to form compact optical circuits by offering large refractive index contrasts. We compare the properties of optical polymers with those of other material systems utilized in integrated optics. We present an up-to-date snapshot of the global effort in optical polymer material development. We describe the criteria that optical polymers need to meet in order to be viable for commercial deployment. We review the state of art in polymeric integrated optical components, including switches, attenuators, filters, polarization controllers, modulators, lasers, amplifiers, and detectors. We further emphasize the practicality aspect by conveying which technologies have been productized successfully, which ones are ready for commercial introduction, and which ones are still under development in research laboratories. Chronological order in the development of polymer integrated optics. Firstly, DuPont, DuPont introduced fiber optics in year 1960. At the same time, glass optical fibers were also introduced. Faced by problems of very high attenuation of order 10,000 decibel per kilometer, application of polymer integrated optics in communication was almost impossible at that time. Mitsubishi Rayon of Japan improved DuPont's technology to reduce the attenuation to 300 kilobytes per kilometer, but still the application in communication was almost impossible. The loss was also quite high. In 1980, graded index POF was introduced. New processing techniques such as swollen gel polymerization helped reduce attenuation problems considerably. In the mid 1990s, the use of POF for short distance, high speed communication was introduced. Presently, there are quite outstanding advances made in the field of polymer integrated optics. which generally include telecommunications and other data transmission equipments. Transmission losses in polymers can be minimized typically by halogenation, with state-of-art loss values being about 0.01 decibel per centimeter at 840 nanometer and about 0.1 decibel per centimeter at 1550 nanometers. The success of optical fiber technology continues to enable great advances in telecommunications. Among the more recent commercial developments include the Embrium doped fiber amplifier, 10 gigabyte per second time division multiplexing, and dense wavelength division multiplexing DWDM. In the near future, two trends will dominate the continued growth of this technology. One, increased optical device functionality, and two, migration of increased bandwidth down to local loop and access levels of the network. Examples of increased functionality includes splitters and DWDMs with increased port counts, wavelength conversion, and matrix optical switching. Migration of bandwidth will require greater volumes of fundamental optical components such as power splitters and WDMs. The research suggested that the polymeric optical device technology, in light of both current and future telecom needs, a series of cross-linked polymers with intrinsic losses in the 1.55 micrometer window as low as 0.1 to 0.2 decibel per centimeter was also developed. Single mode waveguides can be made from these materials by photolithography or by molding. Our baseline materials C20 and C21 are non-halogenated polymers and exhibit waveguide losses at 1.55 micrometer of 1 to 1.5 decibel per centimeter. By increasing the level of halogenation, we can achieve waveguide losses as low as 0.3 decibels per centimeter. These polymers exhibit excellent resistance to adverse environmental conditions, typified by the well-known Belcore 85 degrees centigrade / 85% RH soak test, 1 into 16 and 1 into 8 power splitting devices made from C20 or C21 have exhibited insertion losses of 11 decibels and uniformities of plus or minus 0.3 decibels at 1.3 micrometer. A passive alignment technology that allows optical fibers to be snap fit aligned with the optical waveguide, which reduces the difficulty and cost of pigtailing, was also invented. A secondary case study was taken up by the Allied Signal Inc. USA, wherein a report on advances in polymeric waveguide technologies developed worldwide for the telecom and datacom market was published. Optical polymers are versatile materials that can be readily formed into planar, single-mode, multi-mode, and micro-optical waveguide structures ranging in dimensions from under a micrometer to several hundred micrometers. These materials can be thermoplastics, thermosets, or photopolymers, and the starting formulations are typically either polymers or oligomers in solution or liquid monomers. A number of polymers have been shown to exhibit an excellent environmental stability and have demonstrated capability in a variety of demanding applications. Waveguides can be formed by direct photolithography, reactive ion etching, laser ablation, molding, or embossing. Well-developed adhesion schemes permit the use of polymers on a wide range of rigid and flexible substrates. Integrated optical devices fabricate Integrated optical devices fabricated to date include numerous passive and active elements that achieve a variety of coupling, routing, filtering, and switching functions. Thank you. I hope that I was successful in sharing the information. Have a nice day.